Hi guys. Okay, today we're going to be doing motion formulas, and it's angular motion formulas. Okay, I know you already know the kinematics motion formulas, and we're going to be using those to teach you angular motion formulas. Okay, there's your dad joke over there. Enjoy. Let's go on. I'm going to teach you some of the formulas first. Okay, so let's get started there. So these are the formulas you should already know. Okay, let me bring out my pen here. Okay, so these are the kinematics formulas that you should have learned at the beginning of the year, right? Well, when we're dealing with angular, what we're talking about is we're talking about like let's say a wheel turning and making something move in this direction, okay? And when that wheel's turning, well, what we have is we have, instead of like a linear distance, like here, this stands for a linear distance the wheel has moved, right? That's the linear distance it has gone. Well, as it moves, it also turns a certain amount of degrees, right? Or radians. We use radians in anything that's calculus based. So, like, let's say it turned over here and it stops right here, and let's say it's made one full rotation to get here. Well, it went a linear distance x, and it went an angular distance of, I know this will be easier for you to understand, like 360 degrees, right? But we're not going to be using degrees, we're going to be using radians. And remember, in a circle, the number of radians in a circle is 2 pi. And I know that's a little weird, but it's not that complicated. It's based off of a circle with a radius of 1. And so if you figure out the circumference of that circle, remember to figure out the circumference. Circumference is 2 pi r, and we're just plugging in 1 for r, giving you a a circumference of 2 pi. So like I said, one full rotation is 360 degrees, or for this class, we're going to be using radians, and we're going to say 2 pi radians. And we write rad because radians are super cool and they're rad. Yeah, you get it. Okay, so next thing, let's go over velocity. Okay, so now you get the idea of so linear distance and angular distance is radians. Okay, so instead of x, x we'll call linear distance. Okay, and then theta is what we use for angular. Okay, angular, and you can call it angular distance. It's how many radians it's turned. Okay, so these two are very linked. Yeah, they're the same thing, but one is angular and one is linear. Yeah. Okay, so now let's talk about velocity. Now that is a linear velocity. Yeah, that is a linear thing. So you would take your distance, and you take your distance and divide it by time, and you would get your velocity, right? And that would tell you how far or how fast this object is moving. Well, when we're talking about things rotating, instead of talking about a linear velocity, we're going to be talking about an angular velocity, how fast it's rotating. And instead of it being like here, we used units of meters per second, right? Well, here we're going to be using units of radians per second. So like how many degrees, and I keep on referring it back to degrees because I know you guys are better at thinking of degrees than radians. And if I keep on hitting degree and radian as being similar things, just different units, then I think it'll click. Okay, so we're talking about how many degrees it travels every second, or not degrees but radians, because we're going to be using radians instead of that. And the letter we use for that is a lowercase omega. It looks like a W. You can just call it W for all I care. Okay, but this is angular velocity. Okay, and it's how many, you can think of it as degrees, right? How many degrees it travels every second. Okay, and those two things are linked at the hip too. Okay, so those two are like one and the same. These two are one and the same. And the last thing we need to look at out of all this stuff here is like acceleration. Okay, time time is just time. You can't make angular time or linear time. Time is the same whether you're talking about things rotating or things going in a straight line. So the only other thing we need to talk about is acceleration. Okay, so acceleration, what we've always done in the past is linear acceleration, right? And we measure that by meters per second squared. Yeah? Well, angular acceleration is how fast it's speeding up, right, in radians per second squared. So angular acceleration is not meters per second squared, but radians per second squared. And the variable we use to denote that is a lowercase alpha, and it looks like a little fishy, okay? And those two are linked at the hips. You know what I didn't do up here is I did not write what units these are. Linear distance is measured in meters, right? And angular distance is measured in radians, yeah? So look at the similarities between all of these, okay? So linear distance and angular distance, one is x, one is theta, one is measured in meters, one is measured in radians, right? Okay, look at the linear velocity. It's meters per second. The other angular is radians per second. Linear acceleration is meters per second squared. Angular acceleration is radians per second squared. Okay, so these three things are very similar. And to switch between them, okay, I have that on the next slide, but I think I should just get over it now. To switch between these two things, you just have to multiply by r. Okay, so like let's say, here, I'm gonna give the formulas first. Okay, so like to switch between angular distance, you just multiply by the theta by r, and it'll tell you how far it's traveled linearly. Okay, and I'll give like a little example right now. Okay, so velocity and omega, to switch between those, you just multiply the angular stuff by r, the radius, and that'll give you the linear. Okay, same thing for acceleration and angular acceleration. You multiply the angular one by r, and you get the linear one. So there's three formulas right there you got to memorize. Okay, how to switch between angular and linear. Let's give a little example on how this might work. Let's say there's a wheel. Okay, so we got a wheel, and it has a radius of, I don't know, 2 meters. Yeah, that's huge. It's a giant wheel. It's like a six foot radius. Okay, so it has a radius of 2 meters. And let's say it travels in a linear line, let's say 15 meters. Okay, now these numbers are probably going to come out a little ugly because I'm just making them up off the top of my head. Okay, and I say, well, what I want to know is how many radians did this wheel turn in order to travel 15 meters? Yeah, like it was turning as it was going, right? And how many times did it turn in order to get to the end here? Okay, so what you would do is you just use this formula here. Well, the linear distance was 15. The angular distance is what I want. I want to know how many like radians it traveled, and the radius it has was 2. So then you could divide, and you could get 15 over 2, which is 7.5. And that would be radians. Yeah, 7.5 radians. And if you're like, well, 7.5 radians, what does that even mean? So 7.5 radians, if I told you in degrees, it might make more sense. If I said, oh, like that is 720 degrees, you might be able to think, oh, 720 degrees? Well, that seems like it would rotate. One time would be 360. Okay, another time would be another 360, and you kind of figure out how many revolutions it made, right? Well, 7.5 radians, you can do the same thing. One full turn is 2 pi, right? So what we can do to see how many revolutions it is, like how many times it went around, so revolutions, you could just do 7.5 radians and divide by 2 pi, and then I'll tell you how many times it turned around. So I'm just going to do that real quick, and let's see what the number is. It's 7.5 divided by 2 pi. And that gives us 1.1, oops, I think I need to get my pen back. Okay, That gives us 1.19 revolutions. So it went around one full time and about 0.2, so about 20% of another time. Okay, so that's how you would use these things. And I have problems in the work that go through those, okay? Now, what I want to do is we are going to use all these formulas here, these three formulas, except we want to use them as angular formulas, okay? So they're the exact same formulas, except they're used that we're going to replace the variables with these new angular variables. So anywhere where there's an x, we're going to put a theta. Anywhere there's a v, we're going to put an omega. Anywhere there's an a, we're going to put an alpha. Okay? So watch, let's do that real quick. So like this first formula, we can use it for angular stuff. Instead of linear velocity, to be final angular velocity is equal to initial angular velocity plus alpha, because that's angular acceleration times time. There's that first formula written angularly. Okay, let's do the second formula. Anywhere there's an x, we're going to put a theta. So we have theta equals theta naught. Oops, theta naught. Okay, so this is just this formula. X is theta, and you can kind of think of it as like final. That's how I usually think about this x, as the final. Equals the initial x plus the initial distance plus, okay, velocity, so that would be omega, times time, that's initial omega, times time, plus a half alpha t squared. Okay, there's that whole formula written angularly. Okay, and we got one more formula, we got this one. Okay, and this would be, instead of v, we're going to be putting omega final squared equals omega initial squared plus 2 alpha, because acceleration is alpha, times, now I always think of this, I always replace this whole thing with just distance. It's the distance it traveled. I usually just call it x. So you have two ways to think about it. You could call it theta final minus theta initial if you want to, or you just call it theta. Okay, and there's the three formulas for angular stuff that we're going to be doing, yeah? I do have another formula, another work problem on the worksheet where they use angular momentum, but how about I just, I'll do that on the worksheet if you need it. So look at the final problem that I do in order to see what the formula would be on this, okay? So here's all the formulas you need. You need these three, okay? Those are the angular motion formulas. You need to know how to switch between linear and angular stuff, okay? And then we will do this one on the problems of the worksheet if you need it, okay? So let's try a couple problems. You know what, I'd rather just, let's look at the worksheet. I think that's the easiest way to do stuff, is just start looking at the worksheet. Okay, now this is the worksheet that we have. Okay, and you know what, I didn't put this on a PowerPoint. I'm going to pause it for a second while I can put it on a PowerPoint. I'm back. Okay, put all the the problems from the worksheet onto this PowerPoint. So what I will do is I will work through every single one of them. You can just, I'm trying to get this, I'm trying to get the pen to pop up. Okay, I've copied all the problems from the worksheet onto my PowerPoint, and I'll just go through them one by one. I think you guys should pause it and give it a try before each one, just to make sure you know what you're doing, because that's the most important thing, is that you can do it individually, not that you can do it while I'm doing it, because that's not going to help you if you just follow what I'm doing all the time. Okay, so this is a good example problem though, so you can see how to do one, and then you can do some of the other ones by yourself here. Okay, so we have wheel rotating. It has a radius r, and it looks like some force is being applied on it. Okay, a solid disk of m with radius r and a rotational inertia I. And here's an easy way of thinking of rotational inertia, and I'll talk about it a little bit more later on, is that is angular, okay, angular mass. It's how the object rotates, okay? And so, you know how I said angular velocity is omega. You just multiply it times r, yeah? So angular mass is very similar. It's denoted by I, and it's different shapes are different, masses distribute differently as it rotates. But here's one way of thinking about it. For some objects, it's mr squared. Okay, and so that's just a way to switch between angular, or switch between linear mass and switch it to angular. And it's how the mass rotates, okay? That's what it is. It's how the mass rotates. And we're only going to be using that every now and then. I wouldn't, for right now, I would not get caught up on it. You'll see it more in the future lessons, okay? And we got about 3 or 4 more lessons till we're done with the curriculum, okay? So rotation inertia I is free to rotate about the fixed frictionless axis that is perpendicular to the disk through the center as shown. A force has a constant direction and a constant magnitude F that is exerted on the disk. Okay, so here we go. If the disk is moving clockwise with an angular speed of 5 radians per second. Okay, so that's my initial speed. I'm going to say that's initial angular speed, 5 radians per second, okay? So it's just like any physics problems, we're going to label everything first with an angular acceleration of 1.3 radians per second squared. And that's what that force is doing. Someone's applying a force, or you could call it a torque because it's making it move, it's making it rotate, and it's giving it an acceleration of 1.3 radians per second squared. Okay, what is the angular speed of the disk 3 seconds later? Okay, so time is 3 seconds. Okay, so now we're just going to look at those 3 motion formulas we were given, and we want to know what is the angular speed 3 seconds later. So we're looking for omega f, right? That's our goal. Well, okay, so look back, and you can. I hope you had written down those 3 formulas. I'll write them down real quick, okay? We got omega f equals omega naught plus alpha t, okay? We got omega f squared equals omega naught squared plus 2 alpha theta, okay? And then we got theta is equal to the initial theta plus omega naught t plus alpha t squared over 2. And I wrote a couple of them different. This one on the previous slide was written as theta f minus theta initial, and this one was written as a half alpha t squared. This is how I write all 3 of them. Okay, I'm looking for omega f. Just look at the things that you have and what will give you this. You might have to use more than one formula. In this case, it looks like I can just use this first formula. Yeah, it has everything. So omega f is going to be equal to omega naught, which is 5 radians per second, plus alpha, 1.3, that was the acceleration, times the amount of time. And just use your calculator to do this. And remember, I can't do the calculator on the computer because it deletes the stuff I've written. So I will be using the one in my hand for all purposes. And this comes out to 8.9. Now we need to make sure we got our units correct. This is, remember, angular speed. And speed is meters per second, but we're talking about angular, so not meters, but radians. Okay, there we go. That's our answer, D. Okay, so I hope that helps out. Let's go to the next one. Now, I suggest pausing, give it a try without me, see how you do. Okay. Now, a disk is free to rotate around about the axis perpendicular disk through the center if the disk starts at a rest. Okay, it starts at rest, so that means our omega naught is 0 because it's not moving, and accelerates uniformly at 3 radians per second. Okay, so that's an angular acceleration, 3 radians per second squared. Okay, for a time of 4 seconds, it's angular displacement. Okay, so we're looking for the displacement. So that's angular displacement right there. That's what we're looking for. Okay, so again, you need those three formulas. I don't want to write out all three formulas every time I do a problem. So what I'm going to do is I'm going to look at the stuff I have here and see if I can figure it out without writing it. The first one that comes to mind is I want to use this one, and I'll write them down as I think about them. Okay, I haven't done these problems, so hopefully that will help you out in me thinking. I meant to put alpha here. You can't even tell what that looks like. Okay, so it's omega f squared equals omega naught squared plus 2 alpha theta. That's that third angular problem, yeah? I'm thinking this one will work. I got omega naught. I have alpha. I'm looking for theta. I don't know. This one's not going to work because I don't have this, and I'm looking for this, yeah? So that formula is not going to work. So now what I'm thinking is probably this formula. This is the second one. The second one is what I'm thinking of. Omega naught t plus alpha t squared over 2. Okay, and I'm looking for this. My initial radians we'll say is 0. This is 0, so anything times 0 is 0, so that term disappears. So I just got theta is equal to alpha t squared over 2. And that should work. So alpha is going to be 3 times t squared, so 4 squared over 2. And that'll be 16 times 3 is 64, divided by 2 is 32. Did I do something wrong in my head? So 4 squared times 3 divided by 2, 24. And we're talking about a distance, so that would be meters if it was linear, but we did everything in angular, so this would be radians. So 24 radians. There we go. To the next one. Okay, like I said, pause, give it a try for yourself. Okay, now let's go through it. A disk is rotating at radians per second. Okay, so that's an angular velocity because it's radians per second. 5 radians per second. Okay, at a constant, experiences a constant torque for 4 seconds. Okay, so here, they gave me a time. Okay, now, torque, that's angular force, okay? So basically it's applying some force that's going to make it accelerate. Okay, that results in an angular acceleration of 2 radians per second. Okay, so that's what the torque was doing, is it was making it accelerate, and then they told me how fast it is accelerating. It's the same thing as like if somebody was pushing with 5 newtons of force, well, that thing would be accelerating, right? Well, if someone's applying a torque, making it rotate, it's going to accelerate it in an angular motion. The angular displacement of the disk during those 4 seconds is most nearly. Okay, so it wants the angular displacement, so it wants theta. So it looks like it's going to be using that exact same formula we just used on the other one, yeah? So my initial theta is 0, so I'm not going to write it. It'd be omega naught t plus alpha t squared over 2. Yeah, so it'd be 5 for the amount of time 4 plus the acceleration was 2 for 4 seconds squared over 2. Okay, and then you just type all that stuff in, so it'd be 5 times 4 plus 2 times 4 squared divided by 2 comes out to 36. 36 radians, right? Because it's a displacement, an angular displacement. Okay, there you go. Next one. Okay, we got a turntable is initially at rest. So that means omega naught is 0. Okay, because it said it's at rest. Is it set in motion with a constant angular acceleration of alpha? Okay, so our alpha is alpha. What is the angular velocity of the turntable after it has made one complete rotation? Okay, so if it made one complete rotation, I know it went one fully around 360 degrees or 2 pi radians, right? And it wants to know what is the angular velocity at the end here. Okay, so We just used our formulas again. Yeah, except it didn't give us numbers really. It gave us more variables. So that should make it easier. I don't have to use a calculator. Okay. So I am given, it looks like I'd be using this formula. And guys, remember, I've had the formulas memorized in my head. I'm just jetting through them in my head and trying to see which one has the stuff that I need. And you'll get better at that as you do it more often, okay? You need to be, right now, you need to be looking at the formulas on your own paper that you've written them down on and kind of looking through them and seeing what has what you need, yeah? So I'm looking for this. I have this as 0, so it disappears. And then I have alpha is alpha, and I have this as a 2 pi, right? So if I'm solving for it, I would just square root 2 alpha theta and just plug everything in. So it'd be 2 alpha, theta is 2 pi because it made 1 revolution, and that can be rewritten as 2 times 2 is 4 alpha pi, and it looks like our answer is right here. They wrote it in a different order than me, but that's fine. Since multiplication, it doesn't matter which order you multiply, it always comes out as the same answer, right? Okay, next one. Okay. A wheel of 0.5 radius rolls. Okay, so we got a radius. And remember, pause it, do it yourself. Okay, radius is 0.5 meters, rolls without slipping. The axle of the wheel advances at a constant velocity. Okay, so I know that the velocity is constant. I'm just going to put that here to tell me, okay, it never changes. Moving at a distance of 20 meters, okay, so it went a linear distance of 20 meters. Now notice, I am making a difference between linear stuff, which is measured in meters, and angular stuff, which is measured in radians, right? For a time of 5 seconds. Okay, the angular speed of the wheel about its point of contact on the surface is. Okay, so I'm looking for the angular acceleration. Yeah? Well, first, how about we figure out the linear, did I say acceleration? The angular velocity. How about I first find the linear velocity, which, since it's constant velocity, yeah, is just, velocity is x divided by t, distance divided by time, which is 20 divided by 5, which is 4, right? 4 meters per second. Well, I have my linear velocity now. Okay, you guys know how to switch between linear and angular. You just multiply the angular thing by radius and you can switch between it. So I know this is 4. My angular velocity is what I want. I know my radius is 0.5. So I divide by 0.5 and I'll have my angular thing. So that's just like multiplying by 2. So that's going to be 8 radians per second. If we switched it to angular stuff. So 8 radians per second. Now, you're looking at this and you're probably looking radians times seconds to the -1. What the heck is that? That's not the same units as we wrote over here. But it is. Remember, anything raised to the -1 means you can move it to the bottom and it will now have a positive exponent. So that's the same thing as radians per second. They wrote it weird because they're trying to confuse you, okay? On to the next one. Okay. A rotating platform, remember, pause it, try it yourself. A rotating platform with a radius of 2 meters makes 1 complete revolution. 1 complete revolution. That's what I'm thinking, every 3 seconds. Okay, that's 1 revolution, right? 1 revolution. Okay, the angular velocity of the platform is most nearly. Okay, I'm looking for this. Okay. Okay. So it looks like what I have here is I feel like I just want to do this divided by this to give me what I want, but I don't know here. Two times pi divided by the time, 3. Yeah, okay. So this one's very easy. I was getting a little confused because they're making it a little too easy for me, okay? So so linear velocity is distance over time, just like we did on the last one, right? Well, so if you want angular velocity and it's like constant, like they're making it here, it's theta over time. Yeah, distance over time. Well, theta is 2 pi because it made one complete revolution over the time, 3 seconds. If you divide those, you get 2.09, which is the same as 2.1 basically. They're approximately the same. Radians per second. And there's our answer. Okay. And I avoided even using r. Now, if they would have asked me for linear, like let's say they said, what is the linear velocity? I could have just multiplied this by 2, and it would have given me the linear velocity, which would have been 4.2 meters per second, yeah? And like I said before, like, I mean, this is much easier to visualize. 4.2 meters, we understand what that is. That's 4.2 meters is around, what is that, like 12 feet, a little more than that, like 13 feet every second. Like that's, you deal with those units a lot, so it makes more sense. 2.1 radians per second, I know that doesn't make as much sense because it's how many times something revolved every second. If you wanted to switch it to revolutions, you can just divide it by 2 pi, tell you how many revolutions, like 1 or 2 or 3 revolutions it did every second, okay? But it didn't ask for that. It just asked what is the angular velocity. Okay, next one, an airplane propeller. Okay, so pause it, give it a try. Starts from rest. Okay, and accelerates at a rate of 120 radians per second squared until it reaches an angular speed of, so I'm assuming that's the final, 262 radians per second. Through how many complete revolutions did the propeller rotate while it's accelerating? Okay, look at what it wants. It wants how many complete revolutions, okay? What I'm going to do to get revolutions is I'm first going to see how many radians it covered. Okay, I want this. If I can figure out how many radians it covered, I can just divide it by 2 pi and it'll tell me how many revolutions happened. Okay, so looks like the stuff we have, I want to use this one, I think. That's the third formula, right? I have this, this is 0, so I can cancel it out. 2, alpha is 120, I'm looking for this. Okay, so if you solve for that, it would just be theta is equal to the final angular velocity divided by 2 alpha. And that's going to be 262 squared over 2 times 120. Okay, I'm going to do that in my calculator real quick here. So 262 squared over 2 times 120. That comes out to 286.017 radians. Now that's how many radians it was, right? If you want to switch to revolutions, one revolution is 2 pi radians. So we can just divide it. 286 point, I can just 286. That's so close to 0. I'm not going to worry about it. Divided by 2 pi equals 286 divided by 2 times pi. It's giving me in terms of pi. Okay, the answer is 45.5 revolutions. Okay, so there you go. 45.5 revolutions. Okay. And that's see, like I said, that's much easier to understand. It revolved 45 times, yeah, every second. Yes? Okay. Okay, let's go forward. Okay, the disk initially at rest is acted upon a constant net torque of T. Okay, so remember, like I said, torque is just like it's going to accelerate it, okay? So when they say torque, it's making it accelerate. Okay, the disk spins for a period of time t seconds and rotates at an angular distance theta. The same disk is brought to rest. Okay, the disk is now acted upon with 2 torque. Okay, so more force is applied to it now. The disk spins for the same period of time. What is the new angular distance the disk rotates? Okay, well, if you're going to double the amount of force you apply on something for the same amount of time, you would assume that it would move or rotate more. Yeah, you're applying more force, it should rotate more. So just looking at these, I can already tell you some stuff that I would mark out. Couldn't be that, because that's half as much, but I'm applying more. That's still more. It's not going to rotate the same amount. Yeah, that doesn't make any sense. So it's got to be between one of those three. Okay, so if you apply 2 torque, that means it's going to go 2 alpha faster. The acceleration will be 2 times more acceleration. And the formula, I'm just thinking about this one. This is that first formula, alpha t squared over 2. Okay, that's that very first formula, and it started at rest, right? It says it initially starts at rest, and then even on this one it says it stopped and then it starts at rest again. So this is left out, so you can ignore that because this is 0. Anything multiplied by 0 is 0. So it's alpha t squared over 2. So this is how fast, let's say this is with the torque, just torque, that's how much it moved. Okay, let's say we apply 2 torque. Okay, so it'd be 2 alpha, because it's accelerating twice as fast. It's for the same amount of time, divided by 2. Well, it looks like it's the same thing here, yeah? But we multiplied it by the number 2. So it would rotate 2 theta more. So it would be D. Okay, next one. Okay, an object is rotating in an angular position. Okay, so this is position, and those are the constants. A student wants to represent a different rotating object that is twice the angular speed at every moment. To write a new function, the student should. Okay, so we're going to have a new function. It's not going to be this function, but this function should represent something that has twice the angular speed. Okay, and it's asking what would you do to the variables to make it represent that. Okay, well if I want twice the angular speed, what I want to do is 2 times omega, right? Okay, well they gave me a formula for theta. Now remember PVA, position, velocity, acceleration. To switch between these, you take the derivative, right? To go from position to velocity, you take the derivative with respect to time. To go from velocity to acceleration, you take the derivative with respect to time. To go the opposite, you take the integral with respect to time, right? Well, they gave me position. I want velocity. So let's take the derivative. So velocity, or angular velocity, would be equal to, okay, the derivative of a constant is nothing. The derivative of this, you bring down the exponent, multiply with b, it'd just be b. Plus, the derivative of this would be 2ct. Okay, well if I want to double the velocity, so 2 times omega, right, is going to be equal to 2 times this whole thing. And it looks like I would just double each one of the variables, yeah? I doubled b. This one, the 2 was already there, so I'm not going to quadruple c. The 2 is already there. I'm just doubling it because I'm multiplying it by this 2. So it looks like you're just going to double both b and c, and that will double your the formula for velocity. There you go. Next one. I think I accidentally put that one twice. Oh, I'm missing one formula here. One question. I'm going to pause it and I'll put that one question on. Okay, guys, last question. I'm excited. Okay. A wheel of mass m, radius r, rolls on a level surface without slipping. If the angular velocity is omega, what is the linear momentum? Okay, it wants a linear momentum. Remember, momentum is mass times velocity. We did several units on it. Mass times velocity. Okay, what we have here is we have the angular velocity is omega, right? Well, if I want linear velocity, it's just omega times r, which it told us the r is capital R, so I should probably use a capital R. And there's my linear velocity. So it's just going to be, and my mass is big M. So big M omega r. There's my mass. There's my linear velocity. And we're good. So that would be the first one, A. Okay, there we go. I hope all this helped. And guys, this was all of 5.2. All we have left is 5.3 and 5.4. So next week will be 5.3, and the next week will be 5.4. And we're going to be done with the curriculum. And then we just need to start reviewing, and remember the test will be all free response, okay? So I will start giving free responses, and we'll start doing videos on free responses to really help you guys out, okay? Talk to you later. Bye.